Hello, myself Shami Kumar, and the topic of my research is effect of annealing temperature on the structural and optical properties of the 2D layers of SnSe alloy. Well, we know that thin film solar cells have drawn researchers' attention due to their low manufacturing cost, ease of manufacturing, and less material consumption in comparison to the conventional silicon solar cells. Tin-based binary chalcogenide compounds such as SNS, SnSe, SnSe2, SnTe have gathered global attention due to their abundance, low environmental impacts, besides their potential applications in the electronic, optical, optoelectronic devices, and easy and precise control over stoichiometric to yield high quantum efficiency, unlike conventional CIGSe, CISe, CZTSe compounds. Besides this, binary chalcogenide compounds possesses narrow bandgap energy, high absorption coefficient, and provide brilliant application prospects as optoelectronic devices, thermoelectric refrigerators, supercapacitors, holographic recording systems, thin film photovoltaic devices, and solar cells. And therefore, in order to employ SnSe systems based films for different commercial applications, it is must to promote their mass production with low cost, eco-friendly and easily scalable processes. Keeping this into consideration, different physical and chemical methods have been used to synthesize SnSe alloy films, and thermal evaporation is most commonly used method because it is frugal, non-complex, and offers precise control over thickness, deposition rate, and ratio of impurity contents of the films. Further, annealing leads to steadiness of the deposited films and helps to obtain more densely packed structure, besides providing precise understanding of the nucleation and growth process during thin film deposition. In order to prepare SnSe alloy, highly pure tin and selenium powders were acquired from Alpha Acer and mixed in the stoichiometric proportion of 1:2 in an evacuated quartz ampule at a base pressure of 1 into 10 raised per minus 5 mbar using a vacuum tube sealing unit as shown in figure 1. Figure 2 shows the picture of the sealed quartz ampule containing selenium and tin powders in the requisite proportions. After that, the ampule is put in an automatic temperature control furnace, and the temperature of the ampule was raised from room temperature to 1400 Kelvin in an automatic temperature control furnace at a heating rate of 3 degrees centigrade per minute, while the material kept continuously shaking. This temperature was maintained for nearly 1 hour to allow the materials to melt, react, and settle to attain homogeneity. The ampule was subsequently cooled to room temperature at the same rate it was heated up, which resulted in the formation of solid SnSe ingot. The solid ingot so obtained was crushed to a mean particle size of 100 nanometer using the process of grinding and sieving to have SnSe alloy powder. For thin film deposition, the powder so obtained was used as a source material to prepare 250 nanometer SnSe alloy 2D layers on ultrasonically clean Corning glass substrate at base pressure of 2 into 10 raised power minus 6 mbar in the vacuum coating unit VCU at 300 Kelvin, which forms S1 sample, and at 473 Kelvin, which forms S2 sample respectively. However, 473K deposited samples exhibited better crystallinity than 300K deposited samples, and hence were only considered for annealing under vacuum of 1 into 10 raised power minus 3 mbar for 1 hour at temperatures ranging from 523 to 623 Kelvin in a table furnace as shown in figure 6. Right. The deposition was performed by using single source evaporation method in the vacuum coating unit, keeping the distance between source to substrate fixed at 16.5 cm, while the deposition rate was maintained at 4 to 5 angstrom per second. Figure 7 shows images of the as deposited films at substrate temperature of 300 Kelvin and 473 Kelvin and annealed 2D samples at various temperatures. The color of the samples as deposited at 300K appears to be black, whereas the color of the 473K deposited films appears to be pale yellow, which changes to the brown with lighter shades with the increase in the annealing temperature. Structural analysis. Figure 8 shows the X-ray diffraction patterns of the synthesized powder along with 2D layers deposited at substrate temperature of 300 Kelvin and 473 Kelvin respectively. The XRD pattern of the powdered sample showed presence of strong SnSe2 phase. In addition, peaks of SnSe phase and few weak diffracted selenium peaks were also observed. Thus, the synthesized powder possesses mixed phases of SnSe2, SnSe, and selenium, thus constitute formation of SnSe alloy powder. The 2D films deposited at 473 Kelvin show two prominent peaks of SnSe2 at two theta values of 14.58 degree and 30.60 degree corresponding to 001 and 101 diffraction planes. Beside this, some peaks corresponding to SnSe and selenium is obtained at 2 theta value of 37.82 degree and 24.31 degree for 311 and 1var21 oriented planes respectively. However, the films deposited at 300 Kelvin show prominent SnSe2 peak at 2 theta value of 30.60 degree corresponding to 101 oriented planes along with peaks of SnSe at 2 theta values of 29.69 degree, 37.72, 49.5 degrees corresponding to 011, 311 and 511 oriented planes. In addition, weak peaks of selenium phase was obtained at 24.31 degree corresponding to 1/21 oriented planes. Thus, we can say that S1 films showed absence of 001 oriented while demonstrate preferred orientation along 101 plane. Moreover, the powder sample showed absence of 101 plane and exhibit preferred orientation corresponding to 001 SnSe2 plane. Beside this, the S2 films showed re-emergence of 001 SnSe2 plane along with the presence of peaks that emerged in S1 films. Here, table 1 shows the structural parameters of 2D films at substrate temperature of 300 Kelvin and 473 Kelvin. From the table, we can say that 473 Kelvin deposited films provide overall lower strain value and higher grain sizes than 300 K ground samples. This lower strain value indicates lesser lattice imperfections in the deposited films. Thus, films deposited at 473 K show better crystalline orientations and demonstrate dominating SnSe2 phase over SnSe and Se phase. Table 2 shows the lattice parameters for SnSe alloy powder and thin films of S1 and S2 samples. The cell parameters obtained for the SnSe2 and SnSe phase of the films obtained in case of S2 samples were found close to the reported JCPDS values. Also, the axis strain along A, B, and C axis for SnSe2 and SnSe phase are minimum in case of S2 samples. Thus, we can say that S2 samples demonstrate better crystallinity than S1 samples. In order to study the effect of annealing temperatures on the ground films, the films of S2 samples were annealed in the temperature range 523 Kelvin to 623 Kelvin. The patterns of the annealed films were found similar to that of the powder. However, the prominent SnSe2 peaks in these samples obtained along 101 and 001 oriented planes show variations in the intensity values corresponding to different annealing temperatures as shown in figure 9. The magnified view of the prominent peaks is highlighted in the inset figure. SnSe phase crystallizes preferentially in the 311 orientations at all the annealing temperatures, whereas SnSe2 crystallizes preferentially in the 101 orientation up to 573 and in the 001 orientations at 623. This slide shows the structural parameters of as deposited and annealed S2 samples. The intensity values corresponding to 001 peak found to vary from 137 to 383 with the increase in the annealing temperature, whereas the corresponding crystallite size values found to vary from 18.14 nanometer at 473 Kelvin to 24.19 nanometer at 623 Kelvin. Similarly, the intensity values corresponding to 101 Most significant peak found to vary from 181 to 261 with the increase in the annealing temperature up to 573 Kelvin, and average crystallite size of 101 is found to vary from 11.80 nanometer to 14.06 nanometer. The strain and dislocation density values corresponding to 001 and 101 orientations are found to decrease with increase in annealing temperature. The increase in average grain size indicates improved crystalline behavior of the thin films at higher substrate temperatures, while the decrease in the strain and dislocation values of corresponding films indicates reduction in the lattice imperfections. Optical studies were also carried out, and figure 10 shows transmission percentage as a function of incident wavelength for as deposited and annealed S2 samples. It is clear that as deposited as well as annealed films show low transmittance values up to wavelength region lower than 600 nanometer, which lies in the visible region, and maximum in the NIR region. Figure 11 shows absorption coefficient alpha values as a function of photon energy for as deposited and annealed S2 samples. As evident from the plot, all the annealed samples possess an optical absorption coefficient greater than 1 into 10 raised to 5 per centimeter in the visible region, indicating that the obtained films were highly absorbing, being suitable for photovoltaic applications. It is also clearly observed that samples have a large absorption region that extends to the NIR region. Figure 12 shows the direct bandgap values and bandgap values found to increase with increase in annealing temperature. Since the direct bandgap values correspond to the visible region of the solar spectra, so these films are useful in photoconverter devices. Morphological studies were also carried out, and the same micrographs of the as deposited and annealed S2 samples are shown in this slide. The as deposited films showed uniformly distributed grains along with the presence of flakes throughout the surface. On annealing the films at 523 Kelvin, the micrographs exhibits increased spherical grain growth with the presence of elongulated flakes type structure at the surface. Moreover, an increase in the grain size has also been observed as per visual appearance, and this increase in the grain size at 523 matches well with the XRD results. At 573 Kelvin, the same micrographs show alga-shaped elongulated network kind of structure with the presence of more circular grains. However, a decrease in the grain size has been observed at this temperature, which matches with the XRD results. At the annealing temperature of 623 Kelvin, the film is crack-free and shows uniform distribution of grains. However, the presence of circular grains is not observed at this annealing temperature. The EDX spectrum of the SnSe alloy thin films exhibits that Sn and Se composition strictly depends upon the annealing temperature as shown in table 4. Figure 14 and 15 shows the dependence of atomic percentage of tin and selenium and variation of tin to selenium atomic ratio in SnSe alloy samples with increase in annealing temperature respectively. Table 4 clearly shows that as deposited 2D samples lack selenium during deposition at 473 Kelvin, and tin to selenium atomic ratio varies from 1.17 to 1.55 with the increase in annealing temperature, and atomic percentage of selenium decreases with the increase in annealing temperature due to re-evaporation of selenium at higher temperatures. In order to evaluate the vibrational properties and crystal structure, Raman spectra of the 473 K as deposited and annealed samples were collected in the wave number range 50 to 300 per centimeter. The Raman spectrum of the as synthesized sample indicates the presence of SnSe2 phase along with SnSe phase. The peak observed at 107 per centimeter refers to the EG mode, that is in plane vibration, and the peak observed at 187 per centimeter refers to the A1G mode, that is out of plane vibration of SnSe2 phase. Moreover, the bands located at 75 per centimeter and 155 per centimeter in the 2D samples are nearly identical to group theory predicted bands in age symmetry, therefore indicating the presence of SnSe phase. The variations in the wave numbers of A1G mode and EG mode of SnSe2 phase are attributed to the thermal expansion and lattice strain in the lattice. The wave number corresponding to AG mode of SnSe phase does not show much variation with the change in the annealing temperature. Conclusion. The films of SnSe alloy powders of desired thickness has been deposited successfully. The X-ray diffraction data confirm the formation of SnSe2 phase having hexagonal structure with preference orientation in the 001 directions along with polytypic SnSe phases. The scanning electron microscope images are in agreement with the X-ray diffraction data, and the average crystallized size of the 001 most significant peak of SnSe2 phase varies from 18 nanometer to 24 nanometer approximately. The energy dispersive X-ray analysis indicates that Sn and Se composition to be temperature dependent. The energy band can vary in the range of 1.35 electron volt to 1.42 electron volt. All the annealed samples were found to exhibit an optical absorption coefficient in the range 1 into 10 raised to 5 to 2.6 into 10 raised to 5 per centimeter in the visible and NIR region, indicating the films to be highly absorbing, thus are suitable for photovoltaic and solar cell applications. References. Thanks.